Hello everyone. Welcome back in this session where we are discussing about design of gearboxes for machine tools. In the previous videos, we had gone through some of the points where about talking about introduction of gearboxes, purpose of gearboxes, types of gearboxes, and we have even discussed about need of multi-speed gearboxes in the machine tools, and even we had gone through some points where we discussed the basic considerations in the design of multi-speed gearboxes, right? So now the very important point where we're discussing now, that is laws of stepped regulation of speeds in multi-speed gearbox. So here in multi-speed gearbox, for a fixed single input speed, the output speed between or obtain is between maximum speed and minimum speed, that we could say n max and n minimum, maximum speed and the minimum speed. The variation of the output speed is not stepless but is in the discrete steps, right? So here in a stepped regulation of speed, only certain discrete values of spindle RPM are available on the machine tool. In order to select that discrete step of speed between two extreme values of speeds, there are three laws are proposed. So that is what we are discussing now, the laws of step regulation of the speed in the multi-speed gearboxes. So one first law is that arithmetic arithmetic progression. Second is geometric progression. Third is harmonic progression. So here we'll start with first one, that is arithmetic progression. So we'll discuss now the laws of step regulation of speeds in the multi-speed gearbox. In that, first one is arithmetic arithmetic progression. Here in this arithmetic progression, the difference between any two successive spindle speed, any two successive spindle speeds is constant. The arithmetic progression says the difference between any two successive spindle speed is constant, where second we can say that the calculation of different parameter of arithmetic progressions, we'll see here how do we calculate. So calculation of different parameters for arithmetic progression. So here let or consider n minimum, that we say minimum spindle speed, minimum spindle speed, sorry, spindle speed. It should be in RPM or RPM. N max, maximum, as it says, maximum spindle speed, it's in RPM. We let consider N1, N2, N3 and so on up to the NZ. We could say that different spindle speeds, isn't it? Different spindle speeds in RPM, right? And where in arithmetic, as we said, AT is common difference, as we have discussed here. The difference between the any two successive spindle speed is constant, where AT is common difference of common difference of the arithmetic progression. That is in RPM. And where Z, that is equal to total number of speed steps. Speed steps. Now we'll see what is the common difference of arithmetic progression, or how we do calculate common difference of the arithmetic progression. That we say AT equal to, or you can say step 1, that we said common difference of arithmetic progression, that we say AT notation. So AT is calculated by N max minus N minimum divided by Z minus 1. Right? By this equation we can calculate the common difference of the arithmetic progression. Step 2, the different spindle speeds, where we can say N1 equal to N minimum, N2 we could say N1 plus this difference, common difference of arithmetic progression. This is progression, right? This is what progression. N1, N2 should be progression by AT. So N1 plus AT, or you could say N minimum plus AT, right? So if I say N3, we could say N2 plus AT or n minimum plus 280 and so on. Nz, I can write nz minus 1 plus 80 or that equal to n minimum plus z minus 1 80, isn't it? So now step now we'll discuss about step 3, that is cutting speed for machining operation. How do you that we know cutting speed for machining operation? That is velocity equal to pi dn divided by 1000, where we can say cutting speed, that is in meter per minute, d diameter of workpiece, diameter of workpiece at cutting location, at cutting location, and should be in mm, and n, as we know, is noted it as spindle speed. It's in rpm. So on this equation I could write d equal to 1000 v divided by pi into n. This is cutting speed of machine operations. Now there should be a limit of workpiece diameter, so that is also we need to be considered here in the arithmetic progression. In the step 4, limits of workpiece diameter, where you could say for maximum cutting speed V under the selected machining conditions, the diameter range of the workpiece that can be machined at particular spindle speed, right? Particular spindle speed means we could say that up to nk, means particular spindle speed. We note it, we'll say that nk, particular spindle speed. And if you're talking about limit of workpiece, so there will be a upper and lower limit of the diameter. So we could say upper limit of diameter, that is dk, right? That is workpiece diameter, that is 1000 into v divided by pi into n, as we know, but for particular spindle speed, nk, n1, n2, n3, n4, whatever it may be, d1, d2, d3, whatever it may be, right? Similarly, if you're talking about lower limit of diameter, that is dk plus 1, that is equal to 1000 into v divided by n pi into nk plus 1. So here this is what the step 4, limit of workpiece diameter. Now we'll illustrate one example based on this arithmetic progression. So here we'll take a question. We'll take a question that consider a multi speed drive with with following specifications. What are the specifications given? Minimum spindle speed, minimum spindle speed that have given, that we notated minimum, that they are given like this, or we'll take example of 35 rpm minimum speed, and maximum spindle speed is, that is n max will be 445 rpm. We'll consider, and number of speed, we'll say number of speed steps that we had denoted as z, that is equal to 12 speed steps, where in cutting speed that is v, that is equal to 20 meter per minute. 20 meter per minute. For the given multi-speed drive, based on this arithmetic progression, the different parameters has to be calculated, as we have discussed previous, right? So here, first step, what we need to be calculate is common difference of arithmetic progression, that is common difference of arithmetic progression. That is what we have notated, that is AT, that is n max minus n minimum divided by z minus 1. Here n max is 445, so I'll put n max is of 445 minus n minimum is of 35 rpm, so I'll put 35 rpm divided by z is 12, minus 1. So if I calculated this, I'll get 37.27 rpm. This is common difference arithmetic progression. This is what progression, arithmetic progression in the speed steps, where we'll take step 2, that is spindle speeds. So here we can say n1 equal to n minimum, that is equal to 35, that is equal to 35 rpm, right? N2 equal to n1 plus 80, that is n1 is 35 plus 80 is 37.27. So I'll get 72.27 rpm. Similarly, n3 equal to n2 plus 80, that is n2 is 72.27 plus 80 is 37.27. So we can say that would be 109.54 rpm. This is n3. So similarly, up to n12, we could say n11 plus 80, that is equal to N11 is of 407.7, you could calculate, and plus 80 is 37.27, that is equal to 445 rpm. That is would be maximum rpm. This is minimum and this is maximum. So here we started N1 is minimum and N12, that is 445 rpm, right? Now we need to be calculate ratios of successive speeds. We could say step 3 ratios of successive speeds. So we can say phi equal to n2 divided by n1. N2 we got 72.27 divided by n1 is 35. So I could say n1 is 35. I'll write, and I got the ratio of successive spindle speed for phi 1, that is 2.075. Similarly phi 2, that is n3 divided by n2, that is equal to 109.54 divided by 109.54 n3 divided by n2. This is n2, so divided by n2 here 72.27. So I'll get 1.52. Similarly phi 3, phi 4 and up to phi 11, that is n12 divided by n11, that is equal to 445 n12, and n11 is 407.7, that is equal to 1.09. So this is step 3 where we calculated ratio of successive speeds. Again come to the point of step 4, that is ratio of success, that is have done now ratio of successive speeds. Then now we'll see upper limit of workpiece diameter. So now we can say dk equal to 1000 V divided by pi into nk, right? So we know the values of here. 1000 into V that has been given is 20 divided by pi into nk. So I could write this 6366.198 divided by nk. It's in mm. So now I'll say d1 equal to this 6366.198 divided by n1, that is equal to 6366.198 divided by n1 is 35. So I could say upper limit of workpiece diameter is, that is d1 will be 181.89 mm. Similarly for d2 6366.198 divided by n2, that is 6366.198. N2 is 72.27, so I could get 88.09 mm. Similarly for D12, similarly D12, I could write that 6366.198 divided by N12, N12, that is equal to 6366.198 divided by N12 is of 445. So upper limit of workpiece diameter of that D12 will be 14.3 mm. So you had calculated D1, D2, D3 up to D12, that is upper limit of the workpiece diameter if of step 4. Now step 5. Now step 5, calculate diameter range of that workpiece. Range. So we can say delta dk, that is equal to dk minus dk plus 1. So here delta d1, that is equal to d1 minus d1 plus 1, that is d2, that we can say d1 minus d2. So d1 is 181.89 minus d2 is 88.09, that will get 93.8 mm. Similarly for delta d2, same, d2 minus d3 will get 29.97 mm. Delta d3, d4, d5 up to d11 will get d11 minus d12, that is equal to 1.31 mm. 1.31 mm. So now we'll see the diameter range of different spindle speed in arithmetic progression. We'll make one table and we'll see what is the conditions we had gone through and what are the outputs we have got. So now we'll make a table, or you can say step 6, where diameter range for different spindle speed in arithmetic spindle progression. Now first point is speed steps. Second point we'll discuss about spindle speeds, that we notated nk, that is rpm. 5k, that we have discussed ratio of successive speed, and even we have calculated upper limit of diameter, that we have mentioned in the dk, it's in mm. And another we have discussed the diameter range, that is delta dk, it's in mm. And we'll see how we'll see later remark on the basis of these values, and right. So speed steps, we know that 12 speed steps are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? Spindle speeds, so N1 is 35, N2 is 72.27. We have already calculated this. Here it is. We have calculated N1, N2, N3, and so on. So according to that, we'll put the values over here. N3 will be 109.54, N4 146.81, N5 184.08, N6 221.35, N7 258.62, N8 295.89, N9 333.16, N10 370.43, N11 is 407.7, and N12 is 445. This is what the values we have got calculated. And for K, that is nothing but ratio of successive speeds. 5 1 that we calculated here. 5 1 is 2.07, 5 5 2 1.52, and so on. So we have to be put here. 5 1 is 2.07, 5 2 is 1.52, 5 3 is 1.34, 5 4 is 1.25, 5 5 is 1.20, 1.17, 1.14, 1.13, 1.11, 1.10, and 1.09. Similarly, upper limit of the diameter, the that also we have calculated. Here it is. D1 is equal to 181.89, D2 88.09, and so on up to 12. We'll put all the values over here. D1 181.89, 88.09, 58.12, 43.36, 34.59, 28.76, 24.62, 21.52, 19.10, 17.19, 15.61, 14.30, which is we have calculated, right? And now diameter range that we have calculated. Just a minute. Here it is. Delta D1, the calculated is of 93.8, delta D2 29.97, and so on. So we'll put the values over here. So 93.8, 29.97, 14.76, 8.77, 5.83, 4.14, 3.1, 2.42, 1.91, 1.58, and 1.31. So you can see here on the table, you can see in this table, it is observed that in this arithmetic progression at low spindle speed, the diameter range is very high. The diameter range is very high as compared to the others, right? Is very wide, you can say wide, and hence there is a need to add more speed steps between the calculated values. Whereas at high spindle speed, if you see here, at the high spindle speed, the diameter range is very narrow. The diameter range is very narrow, and hence some of the speed steps are redundant. So on this, the conclusion is what? Where poor its performance of this arithmetic progression is poor in low spindle speed range. So because this is what wide, very wide range in the low spindle speed, right? So what would be the advantage of this arithmetic progression? We could say multi-speed drive with arithmetic progression is good in good in where high spindle speed, in the high spindle speed high spindle speed range, right? That is good enough. What would be the disadvantage? Disadvantage is what? Multi-speed drive in the arithmetic progression is poor in low spindle speed range. This is low spindle speed range. So this is about arithmetic progression, where the disadvantage is where what? The poor in the low spindle speed range. So next class we'll discuss about the next law, that is geometric progression.